When you come to a system and you've diagnosed our compressor is failed and we need to quote to replace, what are some of the things that you guys are considering? Let's see if you miss anything that's on my presentation later.
That it's not flat.
Okay, you need to make sure it's not flat. So you're hooking up gauges, it's good.
Acid.
Acid. Say more.
Checking for acid every time.
Checking for acid every time.
Including that in a quote if you find acid.
Yeah. So doing an acid test. Great. What else? What's some really obvious considerations no one's mentioning?
Surge protection.
Surge protection? No, not necessarily. What else are you thinking about? How about the age of the unit?
Oh yeah.
Okay.
Out of warranty.
Yeah.
Check the
Warranty.
coil for a leak.
Check the coil for a leak. There you go.
On start.
Hard start kit. What are you considering there?
If it's filled.
Okay. If there's a hard cart,
The capacity.
factory hard start kit that's failed or capacitor that's failed. Okay. Cool.
If there's a weird aftermarket hard start kit that somebody put in there.
Yeah. That shouldn't go back in. So first thing we'll talk about is acid. So we need to be thinking about what killed this compressor and how do we make sure it doesn't die again, right? We're quoting this repair. We don't know maybe at that point if the customer is going to go with the repair or maybe a system, depending upon the situation, but you should always assume when you're quoting a repair that they are going to go with it and gather all the information you can. Do an acid test. What causes acid in our system?
Contaminants, moisture, and heat.
Yep. So maybe people putting stuff in the unit that doesn't belong. Could be moisture that was never taken out or that was put in through some carelessness on repairs, things like that. This is why we pull a good vacuum. So just a small amount of moisture stays in the unit and slowly works its way through and turns that oil into acid. And then once we have acid, it eats away, instead of lubricating our compressor, it eats away at our compressor and everything else. Not just our compressor, also the inside of our coil, our TXV components, everything. So it's getting heat. What about heat? Well, how would heat take out a compressor? Or what would heat be related to acid?
Electrical burnout.
Electrical burnout? Okay, yeah, that's true. Didn't think of that.
Makes the oil foamy.
What's that?
Makes the oil foamy and lose lubrication. Like
When it gets hot enough?
yeah,
I don't know what you mean by foamy.
you make the coil.
But it
like
does.
Boiling or whatever.
It does break down the oil when it gets too hot. So once we get like above 300 degrees, then our oil starts breaking down into acid. They say if you measure the discharge line at like 275, then it's probably 300 degrees inside the head of that compressor. And what could cause high temperature on our discharge?
Failed fan motor.
Failed fan motor, dirty condenser coils, yeah.
Low charge.
Low charge.
So specifically what Adrian was talking about, oil foaming is caused by flooded sweat or liquid refrigerant in the compressor. So that's the opposite problem. So overheating causes oil breakdown.
How do we fix an acid problem? All right, so our acid protocol, if we find acid in the system, we're replacing the accumulator. We're adding acid away. And we are
doing that, huh?
We are currently, yeah. Well, maybe there's something to talk about here.
I can't. I'm trying to be quiet. You said acid away.
Objection, Your Honor.
Stabbing me. So can I step in?
Yeah, please
Okay.
tell me about acid away.
Chemical reaction. When you HVAC has physics and chemistry. So if we have acid, right? Acid like the marker. It's bad. Acid in the system. We're like, acid's bad. We want to get rid of the acid. So what do you do to get rid of an acid? Any acid?
Alkali.
Yeah, you add a base, right? Not just trouble, you want the base. So you add base to an acid to neutralize it. So the next thing is, how much base do you add to neutralize the acid?
Don't know.
You don't know, because you need to know exactly how much acid you have so you can add the exact amount of base. How much acid do you have in that system?
No.
You don't know. Unless you poured it all out and you did some time to it, you don't know. So what happens if you add too much base?
You have the same effect.
You have the same exact effect. You guys seen the alkaline coil cleaners?
Yeah.
Yeah, you see them. What does that do to the coils?
Oxidation.
What if you left acid, the alkaline coil cleaner on a coil? It eats it up. You see it foaming on the coil because it's a base is incredibly strong. It's just as strong as an acid the other direction. Like, it is extremely powerful. So when you put too much base in there, what is that doing inside that system? The same thing as doing a coil on the outside. It starts eating it up. Now that's just assuming, let's just assume, because assumptions are to work. Let's assume that we get the exact amount of base in that system. Let's say that we get the perfect amount of base, the perfect amount of acid, just perfectly, just by happening by the tonnage or whatever they say in the bottle, just happened to be perfect mixture. Just in a perfect world, right? It's a lot of perfect going on. If I get the exact amount of acid, exact amount of base, is it a chemical reaction?
Yep.
It is a chemical reaction. It is. That's exactly what happens. When you put a base with an acid, you get a byproduct. It's a chemical reaction. You end up with H2O,
No way.
and you end up with salt.
Oh, shoot.
You end up with salt water. When you're putting base with an acid, you end up with salt water. You end up with salt water in the system. Now, what is that water going to turn into?
Acid.
Acid! It will turn into an acid, and then the salt's doing who knows what to all the moving parts inside that system. You're making it worse. You're worse off than you started for. But it's great marketing. Put this in, it just magically disappears. Anybody old enough to remember the movie Envy? It's like the poo be gone. You just spray the poo and it be gone. The one guy's like, but where does it go? That doesn't matter. It's poo be gone. And then it kills the horse. And anyways, no. Where does the acid go? It just be gone. No, it turns into it be salt water. That's what it be. It be salt water. So you're literally turning that into salt water, which is worse for the system overall. So I went to the people that make this crap. This product, and I was like, hey, you're making salt water. Yeah, but the filter dryers catch it. That was their answer. The filter dryers catch it.
Oof.
Do you know what?
I'm kind of scared because I thought we might have messed them up.
Well, that's you do. But is it catching everything?
No.
Is it actually catching everything? Is there any sitting over here in the base of that compressor? Where's it all going? It's still turning into an acid. They're hoping that the filter dryer will catch the H2O. That's what they're hoping for. Does anybody know the proper cleanup for acid?
New system.
Yes! Filter dryers!
No, new system.
New system. That's true. That's probably what they.
One day
We do filter dryers. We do a suction and a suction and liquid line filter dryers. That's how we do acid cleanup. So what the hell's the purpose of putting this crap in the system if we're gonna have to change the filter dryers to get this crap back out of the system in the first place? We're back to square one. But it's great marketing. Sell this product. This makes everything better.
But would it not get loose if you run it in heat mode?
Oh, well, let's talk about options here for that suction line filter dryer. How long should it stay in the system?
About a week.
Well, no, based on the acid away. Like if they said a filter dryer is going to collect it and you were to run it in heat mode now, so wouldn't it knock whatever loose inside of the filter dryer back into the system?
Well, what's cool about a liquid line filter dryer for a heat pump, we'll do liquid line first, it's easy, is you have these little valve plates on the sides, and then you have your desiccant. And then in the center of the desiccant, you have a hole, and you also got little valves here. Well, actually, I'm gonna start with the regular filter dryer. Regular filter dryer, it's like this, and then you have all of your desiccant, and then there's like a hole inside, kind of, the tube. So all of your refrigerant flows from the outside through the center of the desiccant to the inside chamber and goes forward. That's how a typical filter dryer works. When you have a biflow filter dryer, it always flows from the outside to the center chamber the same exact way. What's changing is the valves here and the valves in the center. So the refrigerant's flowing this direction, this valve closes, these valves open and it goes from the outside in because these valves are closed. So it goes from the outside in. When the refrigerant changes direction, this valve closes, this opens, we go from the outside in, this valve opens and we're going. So either way, we're flowing from the outside in. So even though it's a bi-flow filter dryer, it's always flowing the refrigerant from the outside in, which is super cool. Like it's a super simple design that they make it happen. There's always flowing from the outside in. Now a suction line filter dryer is another topic. If we had to put a suction line filter dryer on in a heat pump in the winter, where could you put it that's always gonna be suction?
Common suction.
Common suction, boom, right there. So we could put it right there and voila, it's always suction. Not on the compressor, no, not on the compressor at all. So the pipe in the middle is always, 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 always suction. Of the three, the one in the middle is always, always, always suction. So you could put it there. How easy is that to get to?
Terrible.
Terrible, horrible. It's a pain in the butt getting there. So yeah, we could do this in the wintertime, but if I can get around it, I personally am not going to. This is just me talking, not Kayla's here, but let's say my idea is when I have to do an acid cleanup, and I'm not going to use the marketing fake crap, I'm going to put me a valve right here on the suction line. I'm going to put me a valve right here on the liquid line. Now we know putting the liquid line filter outside is not a great idea, but if we're doing acid cleanup, I don't want to take everything in the attic to keep changing it out. So what I do, personally, is I put a valve here and here. We already have a valve here and here, correct? So then I put my suction line filter dryer and my liquid line filter dryer there and there, boom, boom. Now I'd have to come back out to check for pressure drop. Already have my ports there. I can just valve this off, recover that last little bit out, put me a new ones in there, and then I can pull a vacuum here and here, and then now, boom, how long does it take to change out a filter dryer if all you're doing is pulling a vacuum in that one little section right there, that little bitty piece right there? Boom, and then you can change it out like every day if you have to. It's like super, super fast. You don't have to worry about pulling a vacuum in the whole system or the coil or anything. One little spot. Now, you can't do that in heating mode, obviously, and you can't leave it there in AC mode because what happens when we reverse? It's gonna take it out. That's right, it's gonna take it out. But once you've got it all cleaned up, you can take that piece out, put your straight piece of pipe in there, open your valve there up. If you so choose, you can move your filter dryer inside, but even if you have to change it again, it's super easy because it's valved off, or valvable off. So yeah, it comes back to acid cleanup, filter dryers. Sorry to take your,
No, that's really good.
I learned about it and I used to use it all the time too. I didn't know, and then once I learned, I'm like, ah.
Yeah, valves are a nice
We've
trick.
been back and forth on it. You know, it depends on, yeah, right. It's yeah, but I agree. Now the valves thing, that's actually a good, and all you have to do is just add that to the kit. We're already getting an accumulator. The other thing that I want to add is that a lot of this comes down to when you pull that compressor out. When you're there to pull it out, let's look at what's going on with that compressor. So you recovered the charge. Was it the right amount of charge that you pulled out? I mean, you have a pretty good sense of what the charge is supposed to be. Was it way overcharged? Was it significantly undercharged? Sorry, we're moving ahead. But then the same thing is also true with the oil. Because if you take that compressor out and you take the new compressor and you weigh those two compressors next to each other, and there's a significant difference in weight, you know that difference is oil. And again, unless you have some different aftermarket compressor or something that's different than the factory one. But if it's the same compressor, which is something you should be paying attention to anyway, is this the right compressor? Take it out, take the one, put it on the scale, put the next on the scale, hey, there's a big difference. That means that that compressor is short on oil. And now we have to think about why was that compressor short on oil. Again, in residential, it's not as big of a factor as it would be in like a commercial application, but still, you're thinking about what causes it to fail. Overcharge, undercharge, improper lubrication. Those are all huge factors.
And what about improper line set, like copper line size?
It can be. And one example would be like a lot of times, here's a fun fact. Manufacturers are starting to, have you seen this? Manufacturers are starting to recommend 5/16 liquid lines again. Bigger liquid lines actually can be more dangerous for a compressor than actually smaller liquid lines in a lot of cases. Smaller liquid lines cause pressure drop, but big liquid lines means that the system holds more refrigerant. And more refrigerant means you're more likely to have flooded starts. So you know, those are factors. Suction line can also play in. Usually that's not a big deal. Usually having a smaller suction line is just gonna reduce your capacity. And in fact, if you look at capacity charts, a lot of times you'll have, we'll say, well, this 5 ton unit needs a 7/8. But if you look at the capacity chart, sometimes a 3/4 inch section line is actually right within range, especially if it's short. So again, the only way to know is to go back to your manufacturer's information. But anything that causes you to have improper suction pressure coming back to that compressor, improper density of refrigerant, improper superheat, those are all going to potentially cause compressor issues. Back to you, Bert.
It's good. Also, when you are quoting that compressor, look around the rest of the system. It may not be the direct cause, but we should, if we're gonna put in a compressor, we should make sure the rest of the system is on point, right? I remember 1 month where I had 2 compressors in that month that had a second filter that was behind the return grill. It wasn't a filter back. It was just return grill. Somebody had unscrewed it, put a filter in there, screwed it back on, and then years later, the compressor failed. Crazy, but really nasty filter in there. And so when I was doing the compressor, going around and looking at everything, and so dirty coils, blower wheel, airflow issues, blower settings, anything that could play into that compressor's failure. And then anything else that just needs improvement in the system. Okay, so you mentioned making sure it's not flat, Adriel. So if your compressor's not running, how would you check refrigerant on a compressor not running?
Standing pressure.
Standing pressure, yep, and
Comparative. It's not all exactly, but I like to reference it to the ambient temperature, just to see. If the indoor fan was off and nothing was actually running at all,
yeah,
then I would use that as to see, kind of gauge whether it's good. If the indoor fan is running, then it's not as reliable because you got something affecting the temperature of the refrigerant.
okay. Yep, so if you said you're looking at what though? You're looking at ambient
and to see, compare with its saturation temperature.
yeah, that's exactly right. So saturation temperature of the refrigerant, standing pressures, ambient. You're thinking about maybe indoor temperature and outdoor temperature, and somewhere in there. It's usually most of your refrigerant's outdoor, so you can match it to outside. If your system has enough refrigerant to have liquid in there, you're gonna have your saturation's gonna be where it should be, close to ambient. If it's low enough that we don't, then you're gonna see this drop in pressures and saturation. And so again, that could be a significant amount of refrigerant missing, but you need to know that before
Yeah, and again,
quoting
like
the compressor.
the thing so here's what I want you to hear. What you said is right, but keep in mind that if you have 1 drop of liquid in that system, it's going to still meet what you just said. And so could you have a system that has 99% vapor and 1 drop of liquid left in it, and is that a properly charged system?
No.
Absolutely not. You could have a system that's 7 pounds low, if it's a system that holds, 10 pounds or 9 pounds, and still have that standing pressure. So the only way to really know is when you weigh it out, right? Which is why we run our electronic over the evaporator coil when we have a failed compressor. So even you confirm it, you're doing that check on the evaporator coil, because we do not want to charge a customer for a new compressor, get it in, and find out that they got a leaking eval, right? And again, you can overdo this stuff. I mean, sometimes we've said, all right, we'll just replace the TXV every time you do the compressor. I mean, it can get ridiculous. You need to tell the client needs to be aware that until we get it running, we don't know everything, but we're trying to take all the proper precautions that we can. But then when you're the guy going out to put that compressor in, you do not just pull the refrigerant out and not pay attention. You weigh it out. It's so important that you weigh it out, because at that point, if you're weighing the refrigerant out, you haven't cut the compressor out yet, right? You haven't done anything catastrophic yet. You weigh it out and it's only got 3 pounds in it and it's an 8 pound charge. Stop. Collaborate and listen. Or listen then collaborate. I don't know. No, just stop what you're doing. Make sure that you go through the system and find the leak, and then talk to the client about that. Hey, I don't want to put this compressor in for you. I know we quoted you for it, but when I pulled the charge out, I found that it was significantly short. That's probably what killed the compressor. Why didn't you do that before? And that's a good question. If you're there and you have it confirmed that you're going to be replacing the compressor, and you can do it right now, which, by the way, we should do more of that, right? Right now, we can do it. Hey, do we got the supply house? Great. Get a driver, bring it to me. I'm going to start pulling it out. You could weigh it out before you had this whole delay, right? This whole weird thing. A lot of this is systematic. You guys are a little overly addicted to punting things to Buddy. I know, I've been reading a lot of calls. Things get sent to Buddy. I don't want it sent to Buddy unless it needs to get sent to Buddy. If you can have that conversation, get a price, confirm, hey, do you want to do it now? Here's the thing, yeah, I really need to get up and running. That's a much more efficient way of clearing the schedule. Doesn't seem like it, but it is. Because it's, we just want to get out of there, right? Text, I'm a troubleshooter. I want to troubleshoot the next job. No, just do it right now if you can. Because that saves that step. Now you can start weighing that charge out. Oops, hold on a second. Stop. Say, call off the driver, go back to the client. Hey, actually, you're also low on refrigerant. This is a bad sign.
Yeah.
You're taking responsibility for the whole problem because it's common. This is not, if this were uncommon, then I wouldn't be saying it, but it's common that it's both, right? What killed the compressor? That's what we have to be thinking about.
Yeah, that's very good. We're talking about the visit there and also our return when we're doing the compressor or if we're starting the compressor same day. So we're checking on initially standing pressure and like you said, only really extreme. I put a question mark on TXV just because you don't have a way to test if the TXV has failed to take it out, but it was to highlight what he said, communicate with the customer that same thing. I don't have a way until I do this repair to know if there was something else that's messed up that played into this damaged compressor. Cool, and this is not a scare conversation, right? This isn't like, I don't know if you want this compressor done because we have no idea if it's gonna work when we're done, right? This isn't some sort of a scare way into like try to push them to do the system. This is, you can communicate this in an honest way. That hey, every once in a while we turn this on and we find out there was some other failure that played into the mix here, right? All right, electrical. So when we are replacing a compressor, we're replacing the contactor and the capacitor. And if it has a factory hard start, we're replacing the hard start with the factory hard start. That's right. So I don't want that missed. 80 point in our process.
I also just want to add quickly here, that's a fine line because sometimes like being able to discern what is a factory hard start and what is not. There are some 3-wire hard starts out there that look like factory. And so you gotta kind of know what you're looking at there. We put a hard start in when the manufacturer suggests a hard start or when it was factory installed. But there's a lot of cases where the manufacturer does suggest a hard start and there wasn't one in it. We should go in with a factory hard start then, especially in long line applications.
Right.
So if you've got over a 50-foot line set, you're working out at Bahama Bay, you're working out at Vista K, and you've got this long line set, then that's when you really need to think, hey, let's make sure we got a crankcase heater. Let's make sure it's wired correctly for the crankcase heater. Let's make sure that if it requires a factory hard start, we put one in. Those are all things, again, this is a lot, right? You guys are like, man, I gotta think of all this stuff. Yes, you do. Yes, this is what it means to be a professional. It's what makes your job fun, right? I heard Austin say, look, I'm already at the point where I pretty much know everything I need to know. And you were talking about that at K Delta. And I was like, I remember being in your exact shoes about 4 years in, because I was a cocky little punk. And then you realize, oh shoot, like there is this like next level. And then you get into building science and then it's the rest of your life, right? Like, and so that's what you do. This is fun, this is challenging. And so, see that long line set? Stop. I'm not gonna say it again like I said last time.
Come on.
Stop. Pull up those installation instructions. Look at what it says should happen for long line, the accessories that are required. It's gonna blow your mind. A lot of cases, it's like 3 different things you're supposed to be doing on this system and nobody does it, right? But if you have a failed compressor, now's the time to do it. The customer has to pay for it, right? Obviously, I mean, sorry, but they would be much happier that we do it now than have that compressor fail again.
Mm-hmm. Beautiful. Why am I highlighting this low voltage here as a possible cause for?
Chatter, intermittent.
That's right.
Short cycle.
Yep, chattering, intermittent, short cycling can be what damaged our compressor. I didn't have a surge protector on here, but surge protectors could maybe protect our compressor, according to Elliot. Mostly because they're actually protecting the components that help the compressor run. So wire damage, you're looking for things that need to be repaired, that need to be cleaned up to add on to that repair or to take care of that day, right? What could have caused this? Poor connections, or high voltage rub out on our compressor plug, something like that, right? Don't be fooled into thinking that it actually is a compressor when it's not. I remember pulling up to a job, my breaker immediately tripping. So I pulled out that little mega meter that we used in the class a few weeks ago. And my compressor read bad, bright red light. And I was like, oh shoot, it's a compressor. Had the whole conversation with the customer. We started getting quotes in the works, and I went around looking like, hey, what else could cause this to fail? And I noticed my capacitor was swollen. Like, oh, that's kind of a big deal. My breaker was tripping right away, and I just went straight to compressor, replaced the capacitor, and everything ran great. Turns out the compressor was not bad. So yeah, wire rub outs. You know, you have your high voltage wire actually rubbing out and causing an issue. It could have taken out the compressor along with it, but it could be a different issue.
Yeah, look at the actual plug.
All right, that's it. Anybody else have something else to add to this? Go ahead.
Why would a failed capacitor make the breaker trip?
Yeah, it's a great question. I should have fully investigated that, but I just replaced it.
Okay.
You can have a shorted capacitor sometimes. It's quite rare, but
It
can
was
happen.
swollen, so who knows what happened inside of there.
Gotcha. Okay.
Probably one of the plugs coming out hitting the edge of it.
I've had capacitors and breakers before.
Yeah? All right.
It can happen. Yeah, they have so inside of the capacitor in the metal shell, there's actually like a plastic coating or a liner, but it can actually, especially when it ruptures, it can actually burn through that and short to the outside. You'll actually see it sometimes where you will have like a black mark on the outside, and that can be a short. It's fairly rare.
All right, it's all you.
All me, okay. All right, so we worked with COVID with major, we call the core reasons for compressor failures. There was 5, and then technically 6, but they called it 5. So anybody know what the main root causes are? Contaminations, yes. Contaminants. Now think of contaminants. What are contaminants?
Moisture.
Moisture, which we just talked about, right? What else?
Also, you could say particulates.
Particulates, yes. Where are particulates coming from?
Copper
Copper
shavings.
shavings.
That's right. Copper shavings. That's exactly right. What's that?
Cooper oxide.
Cooper oxide, yes. I don't know that that's caused compressor failures when I talk to the engineers there, but yes, it is for sure without a doubt a contaminant. Copper shavings they find in the compressors a lot, and that causes a few things. One, you're trying to compress a vapor and you have copper shavings floating around in there, but also that copper can get between the windings and cause that vibration there, especially when that rotor's spinning. It can throw that copper into the side, it can sort it out. But yes, copper shavings, what else?
Non-condensables.
Non-condensables,
That'd be nice.
I guess
that's gonna go with another factor, but yes, I like where you're thinking. What else?
Short cycle.
Contaminants,
Oh,
specifically contaminants. You're right that we're gonna get there, but specifically under contaminants. So when you think, hey, do we have contaminants, particulate matter, moisture, which leads to acid, we'll put acid in there. And anything else?
acid away.
Acid away, additives, yes.
Additives.
Additives, for sure. And there's all kinds of additives. There's people that will market anything. Look, I'm gonna start peeing in jars and say, hey, this is, it's gonna make your system more efficient. You should buy this and put it in your systems, and it's just gonna make everything better. So, there's all kinds of old additives out there. Every time I go to the splash, there's some new scheme. So yeah, contaminants, and anything else you can think of. Dirt. I've seen them where they have dirt in there. Also, soft solder. They find a lot of soft solder inside of compressors. So people that love the Stay Bright 8, they're on like a religion on it, which, it has its place, but people that use it as a religion. You also use flux, and when the system flux can turn into an acid, and then you also end up with the balls of soft solder ends up in the compressor, but also in the TXV. I've taken so many TXVs apart it had soft solder balls in there. So I like to cut TXVs open also to see why did they fail. They're like, oh, these TXVs fail. So I got a guy who brought me a box of them, and I went through every one, and almost every one had soft solder balls inside of it. And it's like, yeah, I've never had a problem with soft solder. I've been doing it for 20 years. I have a box of TXVs from you that says otherwise. Yes, contaminants. Good. What's another main component of compressor failure? Underlining root cause. What's that?
Lock.
Locked compressor. That is a failed compressor. What would cause that compressor to get locked up?
For lubrication.
Poor lubrication. Yes, oil return. And where did that oil go? Where did the oil go? So, like they said, to weigh the compressor, which I didn't learn that until recently, weighing the compressor. But also, I like to drain the oil and look at how much is actually in there. Copeland Mobile app will tell you how much the oil came with that compressor. But also, I can see what's in the compressor. I can see if there's contaminants. I can see if there's particulates. I can see if there's copper shavings or oxidation coming out of it. So I like to drain it and measure it and physically see it. It's just personal preference. Old timer once told me if you go on a roof and you see a whole bunch of dead compressors, the first thing he did was kick them over. We shouldn't just drain a hole in the roof, but he'd kick them over and see if any of them had oil. And he goes, what you'll find is most of the time there's no oil in them, so you're kicking these compressors over and they're all dry. And he goes, the question is, where did the oil go? And everybody says, oh, it just leaked out. And no, oil, very rare for it to just leak out. Where did it go? And it's usually, oh yeah, over here in the evaporator coil. Suction line. An oversized suction line is worse because as the speed of refrigerant slows down, the oil drops out of it. And depending on the slope of that line, your oil ends up back over here in your compressor. Short cycling also can cause oil-logged evaporator coils. Short cycling can be a factor in that. And there's a few other things. There's a whole article in just oil-logged evaporators. Yeah, if your oil's not in the compressor, it's likely in the line set or in that evaporator coil. And that causes poor cooling as well. There's been issues where TXVs have been blamed before because it was an oil-logged evaporator coil. All your oil's in the evaporator coil, it doesn't operate well for the system or the compressor. So oil returns are a really, really big one. Yeah. What else? What other big ones?
I just want to pause there real quick. The vast majority of what we work on here are heat pumps, right? Vast majority are heat pumps. What's the best way to get the oil cleaned out of an evaporator coil? In a heat pump. You just run it in heat, right? So this whole thing of like, oh man, because I know what's going to happen. We have these meetings like, I think it's an oil-logged evaporator coil. Go to evaporator coil. No, all you got to do is run it in heat for a little bit. It'll bring it right back, right?
Wait, that's okay. So I've cut out a number of TXVs that just like spew oil everywhere, right? And it's like the oil will clog, prevent it from operating properly. But if you run it in heat mode for long enough, sometimes it breaks it free. But if it's just clearing the oil, that makes total sense.
Yeah,
Right, that's good.
That's what's happening. That's exactly 100% what's
So
happening.
now we need to solve the oil return problem and not the TXV.
But hold on. What is the number one cause of poor oil return? The number one cause. Suction line sizing can do it. What's the number one cause?
Airflow short run.
Low airflow.
Yes.
Low airflow is the number one cause. Because that also really reduces your velocity. Your suction pressure's dropped. And that's where when you go to that suction, any of you guys are having, you hook up to the suction port and it starts to spewing oil out at you, it's a sign of low velocity. Look at airflow first. And the other things as well, but look at airflow first. Short cycling also.
Absolutely. We're going to jump to the big one being floodback. What does floodback mean?
Selecting the compressor on startup.
On startup? Close. I mean, that's
I'm thinking long lines of
this would be another one, another factor. Flooded floodback. What does it mean? You guys in the back are quiet. I'm going to stand back over here. Floodback, what does it mean?
Tickle them, Ty, tickle them.
What do you say? Yes! Refrigerant back at the compressor. Do we want refrigerant in the compressor?
Yes.
Yeah.
Not liquid refrigerant.
We don't want liquid refrigerant in the compressor. That's right. We don't want liquid refrigerant in the compressor. So liquid refrigerant at the compressor is a very, very bad thing. So what happens when you try to compress a liquid? Boom. Okay. You end up with broken parts. But everybody's like, oh, well, you know, it didn't kill the compressor and I've been doing it this way for 30 years, so, you know, it can't be a problem. And it's not going to typically immediately kill your compressor, but floodback causes damage over time. So in the very bottom of the compressor, this is the base plate. right here in the very center, it looks like it's like a piece of metal, and you're right, it is just a piece of metal, but that piece of metal is actually operates as a bearing. So this is the rotor because it rotates, and the very bottom side of here, there's these little bitty fingers, those are oil pickup fingers, but this sits in the bottom of this plate, just like so, and as this spins, the oil sits in there and it keeps everything lubricated. Then it picks the oil up from the bottom, sends it through the shaft, and the shaft's at a little bit of an angle. You ever take water in a bucket and you sling it around? Okay, one person did. Thank you, sir. Thank you. I'm not the only one that did that. It's centrifugal force, so the oil is being slung and driven through the shaft, and then it's lubricating all of these other moving parts. And it just so happens that all these moving parts need oil. It just so happens we don't have oil return, all these parts are overheating and becoming damaged. Another thing is the liquid floodback. As we start getting liquid refrigerant, the liquid refrigerant is going to go down to the bottom of the compressor. When the liquid refrigerant goes to the bottom, it lifts the oil up. Now, where is that burying it right there? At the bottom. So what's going to happen when we have liquid refrigerants lifting that oil, pushing that oil out of the way?
No loss of lubrication.
You're going to have loss of lubrication. Loss of lubrication, that's right. We don't want loss of lubrication
Amen.
because it's bad. So what's happening right here is we're bringing liquid refrigerant through this whole entire system. But not only that, the liquid refrigerant also washes oil away. So the oil that we already had over all these coatings, the liquid refrigerant washes it away. So when you're having like the, oh yeah, it's good enough, and bad airflow and all that, the liquid refrigerant goes there, starts washing it away from the bearings, washing it all away from all these other moving parts. And yeah, it doesn't kill it right away. It's not like the compressor just goes bang and it's done. It starts washing the oil away. So all these parts start moving with less and less and less oil inside of them. And then you end up with eventually compressor failure. Your motor locks up, and once your motor locks up, or your moving parts lock up, then your windings burn up. So everybody on the tags, oh, electrical failure. It was not an electrical failure. It was a mechanical failure that caused an electrical failure. That's what you saw. So floodback, people say, oh, well, I see it running at zero superheat all the time. It's no big deal. Can't see that it's a big deal, but it's still there. Oil lubrication is a super big deal. Right, we said that, Ryan said we need to recover that refrigerant to weigh it. Because if we don't have enough refrigerant, what is that called? Leak, yes. So what's a sign of floodback? How can you see it gauge-wise, number-wise? We'll go back, sorry, jump it around. Low superheat. Super, whatever. Low superheat. Low superheat. Low superheated what? What is superheat? It's a superheated vapor. Vapor. It's a superheated vapor. We don't have enough superheated vapor. So if I have a low amount of vapor, then I have a high amount of. So here, how much superheated vapor is there in this container? There's no superheated vapor, so it's liquid, right? It's saturation. That doesn't mean it's a full column of liquid coming back, but it does mean that we have a mixture of liquid and vapor. It should be only vapor. So if my superheat's too high, then I have liquid state coming back. How much liquid? We don't know. Now the opposite, what's the opposite of floodback?
Too low. You said high.
Too low.
Yes.
Yep, sorry. So what's the opposite of low superheat? High superheat. So if we have high superheat, what's the opposite of floodback?
Starving.
Starved. Who said starved?
Starving.
Yes, starving. We're starving that evaporative. We're starving it. We're not giving enough refrigerant. So what's cooling the compressor? What's cooling the windings? Nothing. We have nothing cooling the windings. What happens to the compression ratio?
High compression ratio.
High compression ratio. What does that immediately lead to?
Compression failure.
Yes, that's exactly right. But do this in your hands. What do you got going on?
Heat.
You got heat. What do you think heat's going to do to the compressor and all these moving parts?
Burn.
It's going to cause problems. We're going to actually literally melt parts inside of there. But when we get our oil, back to our oil again, when our oil gets too hot, we lose lubricity. It doesn't oil anymore. It doesn't have lubrication properties anymore. And then we continue to get it hot. We actually end up with the oil breaking on down. Breaks down into carbon. We can prove this because Roman and I did this last week in the lab. We cooked compressor oil and we saw it turn to carbon. We saw it firsthand turn to carbon. Well, now we're not lubricating these moving parts, and now we have carbon flakes floating around the system. Where's that carbon going to end up at?
And the cheese.
The TXV. So people are like, oh, replace the TXV when you replace the compressor. It's not because the TXV just goes bad. Sometimes it's simply because that compressor ran with a leak for so long and our compression ratio is so high, we ended up with compressor overheat, which cooked the oil, and the oil carbon got hung up all the way over here, and that carbon got hung up in the screen, usually the screen before the TXV, or in the TXV itself, and that's what the issue is. So it's not that the TXV was bad, it was that the compressor, the evaporator cooler probably had a leak, compressor then overheated, turned the oil to carbon, and then that clogged up the TXV. So a lot of times, it's not that even though the TXV is clogged up, it doesn't mean that that's what killed the compressor. The compressor actually clogged up the TXV. Compressor overheat, yes. And then we have another one is flooded starts. What's an example of a flooded start?
Liquid at the compressor on startup.
Yes, exactly right. That's 100% the liquid in the compressor on startup. That's exactly right. Do we want liquid in the compressor at startup?
No.
No. What's going to happen when we get liquid in the compressor during startup?
You know, can't really turn. It's gonna allow more effort to turn it.
It'll still turn. It'll spin just fine
Slow.
to a point.
It's loud.
It is loud. Yep. What's gonna happen though? If I put refrigerants and oils together, and all of a sudden I start this compressor up, what happens to the pressure in the shell? The shell suction, right? What happens to your suction line when the compressor starts up? It drops. You start the compressor up and the suction pressure does what? Drops. So the pressure in this crankcase, what happens to the pressure when this compressor starts up? It drops. It still drops. It drops. So when the pressure in there drops, what happens to the boiling temperature?
Drops.
It drops. It drops. So the boiling temperature drops. So the refrigerant that's in here with the oil immediately starts to boil. It starts to boil, and as it's boiling, violently boiling. You can take soap and water, put it in a vacuum chamber, and see it. It's like violently. That's what's happening in the refrigerant. But the oil kind of makes encases these bubbles, and so the oil level drops down. So you're getting liquid refrigerant being pumped through here. You're getting oil through here. You're getting all kinds of stuff trying to be compressed inside of your compressor. And then you're trying to squeeze this. What's going to happen?
It's gonna break.
Something is likely to break. Now, reciprocating compressors that broke immediately, but Copeland's had designed a special way to try to help prevent a little bit of this. And what they have done, this one's a little different model. What they've actually done is they designed this to have compliance. So the top will lift just a little bit. And they also have a little bit of back and forth. There's another piece here called a Swedish spring that goes inside there. There's this little Swedish spring of metal that's inside here, that little piece right there, that gives. And this allows it to give just a little bit, and it tries to push the liquid back out the way that it came in. And if it still has so much liquid refrigerant that it can't start up, the idea is that it trips the internal thermal overload to give it time. And it's kind of a bump start. If you do refrigeration, you bump start them 3 times. In the old days, we used to do this in the spring. We'd bump start them to help boil that liquid out, give it time for the oil to settle down again, bump the contactor, let it boil up, let it settle down again. But the same thing's designed in this compressor so that if there's liquid refrigerant, it will trip the internal thermal overload and wait. But there's a thing that people love to sell because it's easy to sell.
Hard start.
Hard start. People love to put a hard start on everything, whether it needs it or not. So the problem is you add a hard start to this compressor. And a hard start adds more what?
Torque.
Torque! Yes, torque! I knew you'd get the torque down, dude. Torque! The compressor has more torque. So now when it's starting up, it's got more torque. So now it's plowing through with that extra torque. So now you have all this extra force going on. You have that liquid you're trying to compress. Guess what happens to these parts here?
Broken.
They end up broken. They end up with all these broken parts. And you can find this on a compressor. Shake the compressor. When you're doing a compressor changeout, shake it. And hear for any of these broken parts floating around in there. And if you do, make sure you clean out the suction line. Use a magnet. Get all these little pieces out of the suction line that's going to take out your new compressor under contaminants. But if you're seeing where you have broken pieces, think, do we need that hard start? And if we're going to have a hard start, what's more important than a hard start is anybody know?
Safety.
C, it starts with a C.
It's on the top.
Crankcase heater. Crankcase heater. crankcase heater is going to prevent off-cycle migration. So when the system cycles off, the crankcase heater stays on. It keeps the compressor oil warm, and it helps prevent the refrigerator. The refrigerator wants to go where it's cool. It's like, hey man, it's cool over there. Let's go hang out over there. It's hot over here in this crankcase, and the refrigerator's like, nah, bro, stay away from that. What's going to get rid of the cool kids are? So if you keep the crankcase warm, you help prevent the oil from migrating to it. When I first moved down into Miami, I would see bad crankcase heaters, and I'm like, you don't need those. You don't need crankcase heaters because it's hot down here. And little did I know, no, you especially need them here too, because outside temperature, especially at night, can drop down. Your refrigerant migrate, especially the units in the attic. The refrigerant will migrate to the outdoor compressor. Next thing you know, especially with a hard start kit, boom. Anyways, that's a thing about how hard starts can actually kill a compressor. Oh, one last thing. If you are changing out a compressor that had a hard start, pull the hard start apart. Look inside of the potential relay and see what the points look like, see what the coil looks like. Because a hard start failing will leave the start capacitor engaged, which will usually blow up the start capacitor first, hopefully, if everything goes well. But it can also burn out the windings in the compressor itself. So a start capacitor, a start kit can actually take out a compressor.
The other thing that I want to mention, because we said we replace the run capacitor and we replace the contactor when we do a compressor. If you take a single pole contactor and you replace it with a 2-pole contactor and you don't pay attention, a lot of times the hard start will not work. So you have to look at what type of hard start it is and how it's wired. Because in many cases it's wired across the open contact. And again, all you gotta do is look at the wiring diagram, you'll see it. Crankcase heater is wired across the open
He's
contact.
saying hard start, but he means crankcase.
I said hard start and I meant crankcase heater, okay? But you all should know that already. I just say whatever I want and you have to interpret it.
I agree with that.
Yes, that was my
said
bad. So a single pole contactor looks like this, right? You have only one set of contacts on it. And there are crankcase heaters that are wired across, and it looks like this usually, something like that, wired across that open contact. And if it's wired that way, and you replace this with one that does this, it won't work. We're not gonna talk about why right now because we don't have time, but I have a whole video on it if you wanna watch that. And so, keep that in mind. Now, in many cases, you can rewire it and it will work, but it's really not designed to. You can do a separate belly band heater that's designed to go on the line side of the contactor, or you can just go back in with a single pole, or you can just wire around with a big gauge wire around these contacts. And that's probably the easiest way to do it, so that way it still operates like a single pole. Okay, just watch for that. It's a weird edge case. I don't know how many of them there are still out there like that, but it's something to pay attention to.
It is, yeah.
There
It's
are.
still,
Okay.
it's still
Still the
common.
standard, okay.
Oh, and just one, there's people that think that just because it has a single pole contactor, they think that it just makes it a crankcase. You still have to have the actual crankcase heater wired around it. For some reason, somebody's like, oh, single pole contactor just makes it be a crankcase heater. I'm like, no, there's a way, but you have to have 2 capacitors. It's ridiculous. But anyways, so you still have to have a crankcase heater. Just because you have a single pole contactor doesn't make it be a crankcase heater. It's not like magic.
Awesome, thanks.
Yay!
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.